This is a pendulum. Everyone knows about them. They're devices that allows weights to swing freely, oscillating back and forth. They have been even used from the 1st century. But have you ever heard of an inverted pendulum before? So, unlike regular pendulums, inverted pendulums are very unstable, and we can test it out. So, try and balance this one. So you can see it's very difficult, but because it's unstable, it's typically used in control theory and control system. And we can try and stabilize it by trying to obtain the mathematical model.
So here, we have a pendulum here. Assume the pendulum is uniform. We have the force acting downward as m times g, and here is the center of mass in the middle of the pendulum. Here is the pivot point. And here's the distance L, which is the distance from the pivot point to the center of mass. So we can use the force U to move the card to the right to counteract the position of the pendulum to up left, and by moving it horizontally to left and vertically up. And to find this coordinate of the center of mass, we can use the equation xg is equal to x plus L sin theta, and yg is equal to L cos theta.
Okay, so next I'm going to explain about the mathematical model. So first we have the net torque, just the product of inertia and the angular acceleration. So here for torque, we need to also consider the vertical torque and the horizontal torque. So then we have the horizontal motion, for which m times the acceleration, because this is the second derivative, and as well as for the vertical motion. And for vertical motion, we have to consider mg due to it being acting on gravity. So next is for the cart, the motion for the cart. We have the second derivative of x, which gives us the acceleration, as well as the mass for the cart. So then we have u minus h, which is, so since u is going to this direction and we want to stabilize this into that direction, so it counteracts. And next, since we need to keep the pendulum on a vertical position, we also need to linearize the equations above. So assuming sine theta equals into theta and cos theta equals to 1, we have this equation. So by having these properties, we can substitute them to the previous equations, the previous 3 equations, to obtain the linearization. So here we have the torque, the horizontal force, and the vertical force, which is 0 in this case. So with the combination of the horizontal force and this force, we find for u. So u is the force in which it moves the cart along the x-axis. So we have mx double dot, m small m x double dot, and ml theta double dot, which equates to u. So now we have the net force and net torque. So as previously mentioned, for the net torque, we have mgl theta minus hl. So since sine theta equals to theta, and here we have L sine theta, we ignore sine, so we obtain for L theta. And then for the equation of an inverted pendulum, it can be described by the following. So we have 2 for the the horizontal force, but in which the cart moves in order to make the pendulum balance vertically, and we have the net torque for the pendulum to be to balance vertically. So here from the diagram, it shows that the force applied to the cart in the direction of u creates a force stabilizing the pendulum. So yes.
Okay, now let us move on to the second problem. This is the system of the second problem. The difference between the first one is that now we put a weighted object at the end of the rod. Assuming the rod is now weightless, the center of mass now falls into the center of the weighted object, with the force downwards from the center of the object is mass times gravity. The length is also different from the first problem, with the center of mass being in the center of the weighted object now, and in the center of the rod. The length is now from the pivot into the center of the weighted object. Now, let us move on to the equation. From the previous equation obtained, which is mass of card times x double dot plus mass times x double dot plus mass times length times theta double dot equals u, which is the force act upon the cart, and for which the moment of inertia of the pendulum about its center of gravity is small, and we assume I equals 0 because it is weightless. Hence, the final formula for this is, which is torque plus torque along x-axis, which is mass times length squared times theta double dot plus mass times length times x double dot equals mass times gravity times length times theta, with it now being mass of cart times L times theta double dot equals mass of cart plus mass times gravity times theta minus the force act upon the cart, and mass of cart times x double dot equals u, which is the force act upon the cart, minus mass times gravity times theta.
So to obtain the transfer function, we just use the Laplace transform on this equation, where theta double dot is the second derivative of theta. So we get s squared, and the Laplace transform of theta is just s. So here we get ml s squared theta, which is equal to mass of cart plus m times g theta minus u. Where here we get the transfer function, which is theta of s over u of s, which is equal to 1 over mass of cart times the length s squared minus mass of cart plus m times gravity. And if we see here, there's the real positive axis and the negative real axis, which means this loop is unstable. And we define the state variable x1, x2, x3, and x4 by x1 being theta, x2 equals theta dot, x3 equals x, and x4 equals x dot. And this state variable describes the motion of the mathematical model's dynamic, for which we only observe the dynamic change of the pendulum's angle and the cart's motion in the x-axis or the horizontal manner. And we can transform these equations into their vector matrix counterpart. So we get here, which is the derivative of xn plus 1. And that's the final answer. And thank you for making it this far. That's it from us.